Okay, welcome to Mechatronics. Today we're going to talk about analog to digital conversion. So here are some of the topics we're going to talk about. We'll kind of introduce uh, discuss kind of differences between analog versus digital, talk about sampling errors, Nyquist's theorem, some performance characteristics for A to D conversion, and then some different devices. Okay, so let's look back at what we started the course with, our mechatronic system block diagram. We've seen this a few times. The focus for today is ultimately we want to be able to get feedback from sensors. And many of these sensors are analog devices. So things that we could think of that produce an analog signal would be like if you're measuring strain from a strain gauge, force from a force transducer, light. We're going to do that in our final project. Some range sensors, we will see that. Those are analog, can be analog devices. Other things we could talk about, there's many others. Sound, could be motor speed, many different things can be measured as analog signals. And if we want to be able to take them in, store them, transmit them with a microcontroller, we need to be able to convert them to digital. Okay, so as we discussed in the first digital lesson, electronics that we're using can only deal with digital values, but much real world information is analog. We talked about this, so we wrote out this list when we were doing digital. Here's some comparison between analog and digital. Of course, analog data is real world. It represents the truth, and because of that, it is higher resolution. But in order to store analog data, more memory is required, and it's more susceptible to noise. Let's talk about that one real quickly. Imagine this is the data that we're trying to transmit. If these are discrete points, if I need to transmit this data, let's say over a radio frequency where we could get interference from other signals, if I'm sending this data point and then I'm just slightly changing the data point for the next time step up to here, and it would be easy to misinterpret that data point on the other end and get a value that's not exactly the true value. So maybe you're getting a data point that's like right there, slightly slightly off. When it's converted to digital and you're sending a binary signal, you're only ever sending zeros or ones. So it's much harder to confuse or misinterpret a zero or a one. It might come across the radio and it's like 0.05. Well, your system is gonna know that's a zero. And when you're sending a one, maybe it's 0.923 or something. Well, your system's gonna know that is a one, and it's gonna change it back to a one. So it's much harder to make a mistake sending only zeros and ones. But when you're sending all this continuously changing data like this, it's very easy to make a mistake. Okay, so now when you do convert it to digital, you have incomplete information. These zeros and ones do not accurately represent what's actually being shown in the real world, and we'll talk about that in a second. Now, on the bright side, digital is much easier to store because we can store numbers as zeros and ones in a much more compact form because, honestly, it's because we don't have the complete information. We have a reduced sample of the complete information. It is less susceptible to noise, as just described down here, because it's harder to mistake a zero for a one or a one for a zero. And it can be perfectly replicated because if we have the exact binary code of that information, we can perfectly copy it. You can never perfectly copy an analog signal. You may or may not have experienced this. When I was a kid, we had cassette tapes, which were recording an analog signal magnetically. And if you had a tape, and you would often, we had these double-decker boom boxes, stereos, and you'd have this um, handle so you could carry it around and play it for your friends. It was really cool. Um, you'd have two tape decks. So you could put in an original and then you could make a copy. And then, of course, this was illegal piracy, but we were just kids and we didn't know what we were doing. We weren't, well, you may or may not have sold them. Uh, so you put in the original and then you could record a copy. The copy didn't sound as good as the original. And then if you made a copy of a copy, it would get even worse. And you made a copy of a copy of a copy, it'd get really bad. So that's because you can't perfectly replicate an analog signal. Okay, let's move on. All right, so let's talk about some problems with digitizing analog information. So here's an example of the red is analog signal, and we are going to convert it to digital, but we can only take samples every so often, a certain at a certain frequency or certain rate. So this right here is like that's your delta t, or your time step. Okay, that's when you're sampling. So only at those times you're recording a sample. The other issue is your the first issue would be quantization error, which is that the digital device can only record discrete values. If the true value falls in between, you'll have a non-zero sampling error. Okay, so if we look at this graph at these points, here it's taken it's taken a sample right here, and then it's going to keep that sample until it gets to the next time to sample. So it's recording a zero all the way until the next time step. That's called a zero order hold. And up here, the signal has gone up, the red line's gone up, and now we're taking the next sample. But you see that corner of that um, digital signal is a little bit higher than the true value. That's because the sampling system can only take measurements at certain spots. We see that exaggerated up here too. And we're seeing an issue here and an issue here where we're not quite getting the right values. The next slide, we're going to zoom in on that. So we're seeing that right here, right here, right here. So this is all quantization error, where we're only able to capture discrete changes in voltage. So we can't always get the true value because the true value might fall in between 2 points where we're able to measure. So that's quantization error. A sampling error comes when we are only taking samples at certain time intervals. So here I'm going to exaggerate this. I'm making like pretty large time intervals. If this is when we're sampling, for example, see this? We're having some kind of dramatic event is happening right here, where the output from the device is going up and then going back down. And if I'm only sampling at these times, I'm completely missing that. Okay, so that's a sampling error due to timing. Okay, the final thing, you've probably heard of this before, and if you're in Mech 460, you've definitely heard of this, but this is called aliasing. So what can happen here is if you're sampling at too low of a frequency, you can get these samples right here where it makes it look like the output is something completely different from the input. So in this case, the system thinks that this big, like low frequency sine wave is the true output when it's actually this high frequency sine wave. Okay, so that's called aliasing. So we'll talk about that on the next slide. Okay, so this guy, Harry Nyquist, was thinking about this aliasing issue and figured out how to solve it. So he proposed this theorem that if we sample at least twice of the highest frequency content in the signal, we won't have aliasing. So we won't get this problem that's shown up here. Okay, so what are we talking about there? Well, let's think about, so any signal could have multiple frequencies within it. We tend to think about, in simple examples, just a simple sine wave. But and that would just contain a single frequency if I drew it actually like a sine wave, more like this guy up here. Real world data signals can have lots of different frequencies in it. Remember from math, you learned about a Fourier series, where you learned that you can create any function, any shape of a time varying function with as a summation of infinite sines and cosines of different amplitudes. These are amplitudes here. So different frequencies, those are frequencies. Whoops, I'm trying to make it an omega, and these are amplitudes here. So if you have these infinite sums, you can create any kind of signal. And these are some cool images from coming from Mathematica that show that you can approximate a square wave. So this is underlying this is a square wave that we're trying to create by summing sines and cosines. So this orange one would be the first term, and then you add a second term, and you get a more a better representation of the square wave. This is the same thing with the sawtooth wave. Okay, so this goes back to Nyquist saying that if you've got something like a square wave, that means you have really high frequency contacts. Remember, as you add more and more of these terms, your frequency is going up. You're increasing your frequency. So something like a square wave has very high frequency content in it. So if you're going to faithfully reproduce a square wave with digital sampling, you would need a very high frequency. So you need to either try to anticipate what frequency content is going to be in the signal that you're sampling, and then make sure that your sampling rate is twice that. Or another approach is if you're not sure what the content is, but you know the capability of your system, you can use a filter to filter out any higher frequency content. So let's look at this on the next slide. So we're still talking about this aliasing issue. Um, so say this is the signal that you're sampling, and you know your system has a certain frequency that it can sample, a sampling rate. Let's say it's 100 hertz, just to be simple. You could create a filter we call a low pass filter, and you can make a simple first order low pass filter with a RC circuit. Okay, so you put your signal in right here, that's the input, and then the output will just be the lower frequencies in the signal. So like I was saying, if you could sample at 100 hertz, you would put a low pass filter with a corner frequency, that's omega C, of 50 hertz. That way you're sampling at twice the rate of any of the content you expect to be in the signal, because you're filtering out any higher frequency content. So that's the anti-aliasing filter. Now, this is a Bode plot. Cadets who've taken Mech 325 or probably other similar courses in other majors have talked about this. This is showing a graph of output magnitude versus frequency. Okay, and what we see here is when the frequencies are low, so this way, frequencies are low omega, we get 100% reproduction of the signal. As frequencies get high, the signals get attenuated, they get reduced. Okay, this is actually a second order low pass filter. I can tell because of this 40 decibels per decade. Now I'm giving you flashbacks for those of you who have taken Mech 325. Okay, so that makes it a second order. All right, so the point being, if you're not sure if you're going to have high frequency content in your signal, you could put in an anti-aliasing filter, a low pass filter to filter that stuff out. Generally, if you're doing data collection, you're going to have filters in there anyway to try to get rid of noise. Noise tends to be high frequency, so we like to filter that out anyway. Okay. Okay, next we're going to talk about the voltage resolution of your sampling system and your analog to digital conversion. So voltage resolution is the number of discrete values that the digital device can accept. You can think of it as the smallest change in voltage that can be measured or distinguished. Um, a good example of this is these two rulers here. So imagine I wanted to measure the length of this blue box. With the top ruler, I could only say it's maybe somewhere between 2 and 3 inches. That's not very helpful. But the lower ruler, it has more divisions, so I can give a more precise answer. I can say, it's 2.5 inches. So more resolution allows you to communicate a little bit more information. Okay, so resolution in an A to D converter is usually described in bits or counts. As in we would say this AD converter is 8-bit or it's 4-bit or it's 10-bit, something like that. Okay. Um, if it has a low count, that means it has a large increment. So of what, like it's delta. Okay. The number of counts is 2 to the n, where n is the number of bits. Okay, so if it's a 4-bit A to D converter, that means 16 counts. A 10-bit is 1024 counts. Okay. Now, we also describe this as the least significant bit, so the smallest distinguishable voltage we can measure, and that is the voltage span divided by the number of counts. So this might be we're measuring a range of 0 to 5 volts, and the voltage span would be 5 volts. Okay, so over 2 to the n. It could be different. It doesn't have to be. It doesn't have to go from 0. It could be 3 to 5 volts. If you were inputting data into, say, well, it just depends on the sensor. There are many sensors. When I described my climbing hangboard device, it had a voltage. I was using a strain gauges that had a voltage range of from 0 to 3.3 volts, which is another common voltage in microcontroller electronics. So the maximum accuracy of your system will be half of the lowest significant bit. Okay, if you think about it, that's the if your, let's say, lowest significant bit, least significant bit is a change of like 0.1 volts. If your true value fell in this range, it could be off by as much as, if this was be 0.1, it didn't come across. So if this was 0.1 volts, your maximum error would be 0.05 volts. Okay, so let's look at a couple examples. So if it's a 0 to 5 volt, I should have put that there, 0 to 5 volt, 4-bit A to D converter, what is the resolution? Well, we can just use this LSB equation right here. Voltage span over 2 to the n. So that's 5 volts divided by 16 counts, and that is 0.3125 volts. Okay. On here, 10-bit. The Arduino Mega has a built-in 10-bit A to D converter. That's really nice. 10-bit really isn't that great. So if we're measuring 5 volt, something that has a 0 to 5 volt range, we've got a resolution of 4.88 millivolts. You'll see that most kind of commercial, well, I shouldn't say that. There's 8-bit AD converters you can buy, 16-bit. One we're going to use in the lab is 16-bit. Okay. Next slide. Okay, I mentioned the Arduino Mega, and there's one way you can do a crude A to D converter using a simple circuit. One reason you might do this, we mentioned, so on the last slide, we said that the Mega had a 10-bit A to D converter, which would give you 4.8 millivolts of resolution. But most microcontrollers are very good at timing, can time very fast. You might have 2 to the 16 or 2 to the 18-bit resolution in timing. So with the Mega, it can measure changes. It can measure the amount of time it takes for events to happen much finer resolution than we can measure voltage output on the A to D converter. So by using a timer to measure a change in something, we can measure every 15 microseconds. So depending on the circuit design, you might be able to measure a lot finer voltage resolution. So what's going on here is we create this circuit where this is your microcontroller, and we have a current limiting resistor. We have a capacitor and a variable resistor in series. So this is your sensor right here. So this would be the thing you want to measure a changing resistance in a sensor. So an example of this would be a strain gauge. It changes resistance as a function of the force applied to it. A photoresistor, it changes resistance as a function of the amount of light falling on it. We're going to use photoresistors in the final project, and you've used some already in the lab. This could be a photoresistor, and you hook up this circuit. Basically what you do is you charge up the capacitor from the output pin. So this is an IO pin on your microcontroller. So you charge up the capacitor, then you set this pin to input mode so that current doesn't flow into the microcontroller. Then you allow the current in the capacitor to discharge out through this photoresistor. Now, depending on the status of the photoresistor, how much resistance it has, this is either going to discharge quickly or discharge slowly. And we're measuring the length of time it takes for that capacitor to discharge. So that's your delta T, and that corresponds to the resistance in the photoresistor. That's a simple way to do A/D conversion. We actually used to do a lab in this. We are not doing it this year. Okay. Okay, when we describe A/D converters, there's a few different performance characteristics we want to be aware of. Okay, the first one is monotonicity, and this is we want to make sure that if there's a positive change in the input voltage, that we are always getting a positive change in the digitized output. So if this is in and this is out, it doesn't necessarily need to be a constant slope, but it needs to be always going up. If we had something that went like this, that would mean I could get a increase in the input voltage. Like if this was the input voltage, let me do this first. So let's say this is VI and this is VI plus 1. And I'm at VI, I've got a certain output of V out, and then at V out I, and at VI plus 1, my V out has gone down, even though my V in went up. So V in went up and V out went down. That would fail the monotonicity test. Okay, this is not really an issue with modern A to D converters, but it's something you want to think about. Now, another issue is maximum sampling rate. So we've talked about that. Here, I'm talking about what is its sampling frequency. So is it like 1 hertz, 100 hertz samples per second, 1,000 kilohertz, etc. You're going to pay more for a higher sampling rate. You also may get lower resolution. There's usually a trade-off between resolution and sample rate. And it has to do with how we actually take the measurements. Okay, if you're recording more bits worth of information, it just takes more time. Okay, so many ADDs can be temperature sensitive. Capacitors are temperature sensitive. If your ADD method has capacitors in it, it's going to have some sensitivity to temperature. The method I just described in the previous slide with the Mega, the kind of the crude hobby way to make an ADD converter, it's very temperature sensitive. Modern ADDs have a way to get around those issues. We'll talk about that in a second. Gain error and linearity are a couple different issues. So one issue I kind of alluded to up here. So linearity, you might have a system that has what looks like, so this is, I've drawn kind of like an exponential type of slope. It's not linear, right? Linear would mean a straight line. That would mean that when we talked earlier about the least significant bit, so that a change in voltage in is going to have if this is 1 bit here, if it's linear, 1 bit is going to have some delta V, and that's always going to be constant. Well, if it's nonlinear, that's not true. As we get, each successive bit could have a greater change in delta V. Now we can account for that in software if we know that it exists. Gain error can be a different issue where your values may change and it's not necessarily consistent. Where the slope, this slope here, isn't constant and it's inconsistent. So in the first example with a non-linearity, the slope wasn't constant, but it was consistent. So at least it's easily predictable. A gain error could mean it has a non-constant slope and it's inconsistent. I wrote consistent, but that should be inconsistent. Okay, I guess I meant isn't consistent. Let me just to be perfectly clear, and isn't consistent. Okay. All right, so let's look at a couple A to D converter designs. The most basic is called a single slope, and there's a picture of that down here. This is fairly easy to understand. What we do, so this device right here is called a comparator, and we are not talking about op amps in this class. Anytime you see this triangle, this is an op amp. So if you're a double E, you've seen plenty of these and you probably hate them. If you're a mech major, we talked briefly about these in Mech 325, if you've taken Mech 325. But op amps can be used to do various things. This particular op amp is a comparator. So its job is to compare two voltages, and it will output a 1 or a 0, depending on if input is higher or lower than the reference voltage. So like this is a reference and this is an input. So we're just comparing these two signals, and we get 0 or 1 if one's higher or lower. Okay, so just imagine you're comparing. All right, then we have this voltage source, and we're creating a ramp right here. Okay, so we're going to make voltage ramp up at a constant rate, so with a constant slope, and then we're comparing here. So if this is our sensor here, this is the voltage we're trying to read in, And this voltage here, this is the ramp. It is just increasing at a constant rate. So when it starts out, the ramp is going to be lower than the sensor value we're trying to read. It's ramping up, and at some point, it's going to hit the same voltage as the sensor. So that this line is right here, this dashed line. At some point, we're going to hit that, and the output of this comparator is going to switch. So let's say it started as a 0, and then it goes to a 1. When that happens, we record that value and we say there's our output. Now this is more complex in a real system. This would be like a counter, a binary counter or something like that. But it's basically going to say it's going to output once those two voltages are equal, and now we've measured the voltage. So we have our V out, our sensor value. At the same time, this is, you should recognize this. This is a FET, okay, a MOSFET. This control logic is going to tell this to open this path, and the capacitor will drain out so that we can start again with another ramp up. Okay, so that's a very simple way to measure an analog to digital conversion. There's more details on this in the book. This image is from the book. So drawback to this method, if it's simple and pretty reliable, it takes time because we have to do this ramp up process, and we're using a capacitor, and we mentioned capacitors can be sensitive to temperature. So we want to try to avoid those issues with capacitors. So another option is called a dual slope. It fixes the capacitor issue. So I don't have this actual circuit for a dual slope. It's similar to the last one, but it's the process that's used to measure is slightly different. In a dual slope, you charge up the capacitor to a voltage that is proportional to the voltage you're trying to measure. And then you actually are doing so this charging phase, we're not actually taking a measurement. It's just getting ready. So this is just prep. And then we actually take the measurement, we charge up the capacitor, and we discharge. So over here, we're discharging the capacitor. And because of the way the circuit is designed, the current is constant as we discharge with constant current. And as a result, the time it takes to discharge, T, will be directly proportional to the voltage that the capacitor was charged to, which was proportional to the input voltage. So this is just a more reliable way to do it. Basically what it does, because you're doing this prep phase and this discharge phase, we're factoring out the capacitance of the capacitor. It really doesn't matter what the capacitor is doing. It can be changing as a result of temperature, and you'll still get a consistent measurement. Okay. This is the particular A to D converter we're going to use in our lab, the ADS 1115. Just some information about it. I thought it was interesting. This is a delta sigma converter. This operates in a completely different way than what I just described. If you want to know more about it, it's in the book, section 19.5.5. It's basically doing some comparisons similar to what I described, and then recording how close it is to this, sort of making an educated guess about what the output is supposed to be, comparing that, and then refining the guess over time. This particular one can do 2 to 5 volt operation. So that means its power can be anything from 2 to 5 volts, and its output, basically, it's going to be giving you bits. Those could be anywhere from 0 to 2 volts to 5 volts. So obviously, if we're running this in the Raspberry Pi, we want to use the 3.3 volt operation. That means on our VN pin, we're going to give it 3.3 volts, and we're going to give it ground, and we're going to get, there's ground right there. And that means on the output, the digital output will be 0 to 3.3 volts. All right, this one has 16-bit precision, so that's pretty good. It's going to use I2C communication, which we know all about now. It has 7-bit addresses. So now it has, what are the addresses for? We have 4 channels available on this device, and these are here, A1, A0, A1, A2, and A3. If you're reading, you need to read off of a certain channel, you'll have to tell it in code which address to use to read which channel. It can sample anywhere from 8 to 860 samples per second. This is really slow. A really good A to D converter could get up to the megahertz range. So we're not even hitting a kilohertz. But this is also really inexpensive. It has some built-in reference voltages, which can be useful, especially if you're doing something like a strain gauge. You need to have a reference voltage. Another really cool thing about this, it has a gain amplifier. So those of you in 460 that did strain gauges, you've amplified the strain output because strain output from a Wheatstone bridge is very, very small. So because of the gain amplifier, it can take in voltages as low as plus or minus 256 millivolts. And when you multiply that 16 times, you're going to have plus or minus 1 volt. Okay. Now I'm going to say real briefly, just talk about the entire lesson has been about analog to digital. A quick note about digital to analog. So one D to A method you're familiar with already is pulse width modulation. So we've talked about this before. And this is where we're approximating an analog output by sending out a rapidly changing digital output. Okay, this is common to all microcontrollers. You can do it on the Mega, on the Pi, anything else, because it's very easy for a digital device like that to output highs and lows and do it very fast. Now, in many cases, you don't want these completely on or completely off, rapidly changing voltages. So a common way to deal with that is to put a filter on the output, so a simple RC circuit, to create a more closer to a consistent signal, and that's what's shown right here. So in this example, this is from the book. This is a 1 kilohertz PWM signal, meaning that these are going on and off at 1,000 times per second. It's a 50% duty cycle, which you can see from the picture. It's looks pretty close to 50%. It's 0 to 5 volts peak to peak. Now it's been smoothed with a 100 hertz smoothing filter. Even in this example, to our eyes it looks pretty flat, pretty straight, but it still has a 78 millivolt peak to peak ripple going on here. So that's like this difference here. And depending on what you're doing, that might be problematic. So a commercial B2A converter will do better than that. Now, in general, if you're going to use a smoothing filter on your PWM, you'll get less ripple if there's a bigger difference between your PWM frequency, that's like this 1 kilohertz, and your corner frequency of your filter. So in this case, I wrote it's 10 kilohertz, not 1 kilohertz. We have 10 kilohertz over 100 hertz. So that's 100, a ratio of 100 for the ratio between our PWM frequency and our corner frequency. You can get that ripple smaller by having a bigger ratio. Now, the problem is if you put a filter on there, you're slowing everything down. So this slows the response time. So as usual, there's a trade-off. There's a trade-off between the response time and the amount of ripple. All right, so there's many other types of D-to-A converters. If you'd like to learn more, look in your book, look on YouTube. That's all we have for today. We will do some of this in the lab.